So today I'm here as a representative of the WIPP performance assessment team that's based in Carlsbad, New Mexico. And the waste isolation pilot plant performance assessment is in the process of being updated to use a 3D conceptual model. And the work that I'm going to describe today is kind of the end product of a couple of years effort by many, many people. And only 4 people made it on as co-authors to this report, one of whom is Jen Frederick sitting in the back there. But the whole team in Carlsbad was definitely involved in this work. So for those of you who have forgotten or maybe didn't know, the waste isolation pilot plant is a deep geologic disposal facility for transuranic waste from around the DOE complex. It's located in a bedded salt formation in southeastern New Mexico. And so I'm going to talk about that transition to a 3D conceptual model for performance assessment. I'm going to tell you about the development of WIPP flow mode in PFLOTRAN, which will be the subsurface flow and transport code in the new future PA, and about verifying the PFLOTRAN development by comparing to Bragg flow, the current flow code in WIPP PA. So on the left here is a diagram of the current WIPP repository layout. The waste disposal panels are in green at the bottom of the diagram at the south end of the repository. And the important thing to notice about this repository layout is that it basically has a 2D symmetry to it, with the mirror plane running north-south vertical in this diagram. Above the disposal panels, you can see the operations area. And then there are shafts for ventilation and access. And then up here at the northernmost end of the repository is the experimental region. So when WIPP was closed, ground stability began to be a problem in the southern end of the repository. And although panels 3, 4, 5, and 6 already have waste placed in them, it was decided to abandon panel 9 here in the middle. It will never have waste placed in it, and waste emplacement then needs to occur somewhere else. There is a proposal to add new drifts somewhere to the west of the existing drifts, and if that happens, then the 2D symmetry of the repository will no longer exist. On the right of this slide is a diagram of the 2D grid that is currently used in flow and transport calculations for WIPP PA. This repository is represented in some very small grid cells right here in the middle of this diagram, and it's flipped. So north is vertical in this drawing, north is to the right in the 2D flared grid drawing, and the repository lies right in there. And then the flaring of the grid represents 2D radial concentric flow. There's additional flaring inside of the repository itself that accounts for the volumes of the different regions of the repository. Here's a diagram of the current codes that are used in WIPP PA. And let's go ahead and get that on there. So Bragg flow is the 2-phase flow code that's used on that 2D grid to simulate flow in and around the repository. Output from Bragg flow, pressures, volumes, and the flow field itself is passed downstream to other PA codes. So some of those, like those up here not outlined in red, just calculate direct releases at the time of borehole intrusion to the surface. And then these outlined in red, panel and nuts, are radionuclide mobilization and transport codes. And nuts operates on that same 2D flared grid that Bragg flow does to model radionuclide transport in the near and the far field. All 3 of these codes, Bragg flow, panel, and nuts, will eventually be replaced with PFLOTRAN. A little bit about PFLOTRAN, which I know many of you are already familiar with. It is an open source, state-of-the-art, massively parallel subsurface flow and reactive transport code. And this massively parallel part is important because when we go to a 3D gridded model domain for WIPP, we expect the problem to become much larger, and the parallel computation will be necessary in order to perform PA in a reasonable amount of time. It does 3D domain decomposition with PETSI, which is a library out of Argonne National Lab. PFLOTRAN itself has developers at many of the national labs. It exhibits strong scaling to over 10,000 cores, which means that given a problem of fixed size, when you double the number of cores, the wall clock time per time step is decreased by a factor of 2. PFLOTRAN, prior to the WIPP development, already had several different flow modes in it. So the point I want to make is it's not weird to be adding a new flow mode for specific use at WIPP. And some of those flow modes that are in common usage are the Richards flow mode for single-phase variably saturated flow mode. We use TH, which is Richards equation plus energy, and general mode, which is full multi-phase air-water energy. In our generic disposal systems analysis work package, and some of these other modes are used for carbon sequestration. And, you know, I think it may not have made it on here, but there's also an oil and gas mode. PFLOTRAN is used widely actually around the world, and its uses include biogeochemical modeling, CO2 sequestration, modeling of geothermal systems, and modeling of oil and gas reservoirs, and of course modeling of nuclear waste repositories. So a couple of the uses that you may be familiar with. This one, if you were listening yesterday, you are familiar with the Geologic Disposal Safety Assessment Framework and our generic reference cases. It's also used to model uranium migration at the Hanford area, and that work is out of PNNL. So the objectives of the PFLOTRAN Bragg flow comparison were first just to verify that in WIPP flow mode that two-phase immiscible flow is implemented correctly, and also that all of the many WIPP-specific process models were implemented correctly in PFLOTRAN. We wanted also to verify that PFLOTRAN performs robustly over the entire sample space used in the WIPP-PA flow calculations. And we'd also like to quantify the differences between Bragg flow and PFLOTRAN so that we can minimize the effect to PA calculations from the code transition itself. So the scope of this comparison involved quite a lot of development work inside of PFLOTRAN. It also involved comparing the two codes on a suite of 0D, 1D, and 2D test problems. Those I will not tell you about at all today. Instead, I'm going to focus on the comparison of the two codes that was done on a suite of 1,800 simulations that are essentially the same flow calculations performed for a WIPP-PA. Development of WIPP flow mode in PFLOTRAN involved implementing two-phase immiscible flow without an energy equation in there. Coupled into that two-phase immiscible flow, fully coupled into that, are several WIPP-specific process models. And those include a gas generation term and a brine term that could be either consumption or generation due to things like corrosion of the waste packages and biodegradation of any organics in the repository. There's also MGO in the repository that is intended to suck up brine. Creep closure of the waste areas is included in the process models. Fracture opening and closing in the marker beds in DRZ due to changes in liquid pressure. There is a soil compressibility model that is simply soil compressibility, but it's special for WIPP. It was not the same as what was already in PFLOTRAN. Same with the characteristic curves relating capillary pressure to liquid saturation and relative permeability to liquid saturation. Those are special for WIPP, so they were all added. The Klinkenberg effect on gas permeability and a new gas equation of state were also put in there, fully coupled into the flow solution for use in WIPP-PA. Additionally, the ability to change material properties at any specified point in time was added to PFLOTRAN, and that capability is used to model evolution of the disturbed rock zone and the shaft properties, and also to model borehole intrusion and the evolution of the borehole properties through time. So in addition to simply, and I'm going to put simply in finger quotes, implementing all of those WIPP-specific process models and coupling them directly into the solution of the flow equations, there was quite a lot of behind-the-scenes development that needed to go in to PFLOTRAN in order to achieve the level of agreement between the two codes that I'm going to show you later. And that includes things like making sure that the convergence criteria used in Bragg flow and in WIPP flow mode in PFLOTRAN are the same, that the perturbations used to calculate numerical derivatives in pressure and saturation are calculated the same way in both codes, that limits on saturation and on liquid pressure and how that affects Newton iteration behavior need to be the same between the two codes. Same thing, limits on saturation and pressure affect time step size. The Jacobian has a particular type of scaling applied to it, the maximum number of Newton iterations, the maximum number of time step cuts allowed, and the way in which time step is ramped either as it's increasing or decreasing. So these things were all made to behave the same way in PFLOTRAN's WIPP flow mode as they do in Bragg flow. And I would just like to point out that not on this list of development efforts, the order in which you check all of these criteria matters to the solution you're going to get. The order of operations inside of each of those WIPP-specific process models matters to your numerical solution, as does the behavior of the process models during Newton iteration. Another special thing that Bragg flow did is fixing the upwind direction during Newton iteration so that the relative permeability can't flip back and forth while you're iterating. So that was implemented inside of PFLOTRAN. And some things were also implemented inside of PFLOTRAN specifically so that we could do this comparison on the 2D flared grid. And that includes the way the transmissibility is calculated, where you have grid cells that do not share the same surface area adjacent to each other, and elevation correction that accounts for a 1-degree dip in the Salado, and also the addition of cell-centered boundary conditions to PFLOTRAN. So the WIPP-PA flow calculations explore 6 different scenarios. And on the right is a drawing of the conceptual model that covers a couple of those scenarios. And in the, oops, hold on, back. So in this drawing, you can see the waste disposal region here in gray. This is the shaft, so ops and experimental areas would continue off to the right of this picture. Below the waste disposal region, there are, trying to think where, there is a marker bed, which would be clay and anhydrite layer of higher permeability than the surrounding salt. There's another anhydrite layer above it and another clay anhydrite marker bed above that. What else? So this thickness right here is the Salado. Beneath that is another salt formation called the Castile. There's a possibility that there would be an overpressured pocket of brine sitting in the Castile. So that's drawn into this conceptual model. And then this particular scenario considers the possibility of human intrusion by somebody drilling directly into the borehole. And so the potential paths for radionuclide release in this scenario are simply through the repository to the shaft. Up the shaft could go to the surface, but what we'll actually consider is that it could go into an aquifer, the Calabra, that lies above the repository and enter somebody's groundwater that way. Another potential path for release to the accessible environment is that radionuclides could transport through the disturbed rock zone to the marker beds above or below the repository and travel through the marker beds to the land withdrawal boundary. And then the final potential path for radionuclide release is directly up this borehole. So we're not going to talk about the codes that model the direct release at the time of borehole intrusion, but we are going to consider flow up the borehole when the borehole seals fail, and that could be a source of radionuclide transport to the Culebra and from there to the accessible environment. So that's just one possible picture. Otherwise, conceptually, scenario 1 is undisturbed. So in scenario 1, you have the conceptual pathways, including the shaft and the marker beds, but no borehole intrusion. Scenario 2 includes borehole intrusion into the repository, hitting that pressurized brine pocket. Scenario 3 is intrusion at a later time, but again, hitting the overpressured brine pocket. And then scenarios 4 and 5 include borehole intrusion into the repository without hitting the pressurized brine pocket. So the driving force for flow upward is much less in scenarios 4 and 5 than in 2 and 3. And finally, the sixth flow scenario that's considered has intrusion of a single borehole at 1,000 years, not hitting the overpressured brine pocket, and a second intrusion at 2,000 years that does hit that pressurized brine pocket. And we're going to look at results for simulations of all of these. For each scenario, there are 3 replicates of 100 simulations each, for a total of 1,800 simulations. This is looking at that 2D flared grid. It's the vertical section of it. And rather than drawing unequal area grid cells, every grid cell in the grid has just been drawn as an equal area square. And what I want to show you on this picture is the points of comparison that we use to compare the 2 codes. So inside of the waste area, which is the panel, the waste panel that borehole intrusion occurs, inside of the waste area, the south rest of the repository and the north rest of the repository, we compared volume, weighted average liquid pressures, and liquid saturations. Those are the areas that actually contain waste. We also compared volume, weighted average liquid pressure and saturation in each of the 3 panel closures in the operations area, in the 3 cells of the shaft that are at the level of the repository, and in the experimental area. And then we compared liquid flow across the south and north land withdrawal boundaries in the 3 marker beds. And we compared liquid flow, vertical liquid flow to the Culebra from the borehole and inside of the shaft. For now, I just want you to trust me on the results of the simulations, and I'm going to tell you that the borehole ends up being the only potential release pathway where the liquid flow away from the repository is large enough to advect radionuclides to the accessible environment. And I'll show you a figure later that, that actually demonstrates that. And the borehole flux is large enough to carry concerning amounts of radionuclides occur only in scenarios 2, 3, and 6 when the borehole hits that overpressured brine pocket. So those are the scenarios that we're going to focus on. Although we made the comparison for all scenarios, I'm only going to show you results for scenarios 2, 3, and 6. And I will show you comparison results both in terms of quantified time integrated differences and uncertainty distributions. So we quantified the difference between the PFLOTRAN and the Bragg flow results for every single one of those 1,800 simulations at all 9 locations in the repository and all 8 of the flow comparison locations. And the way we did that was by integrating the difference between the 2 curves. So in this plot, X would be time, Y is your quantity, either the average liquid pressure or saturation or the liquid flow across a plane. And we quantified the difference between the 2 curves by integrating the absolute difference between the Bragg flow and the PFLOTRAN solutions as a function of time. For liquid pressure and saturation, that number was divided by 10,000 to return a value comparable to liquid pressure or saturation at any given time. And for liquid flow, that value was not divided, so this difference would be comparable to the cumulative flow at 10,000 years. And then we also calculated relative difference, and I'll actually focus a little bit more on that in the following slides, by dividing the integrated difference by the area under the Bragg flow curve in both cases. So this is, for example, what does that information give us? It enables us to take a complicated horsetail plot, which is shown on the left. This is the volume average liquid pressure as a function of time for replicate 1, scenario 2 in the waist area. I'm wondering, can you see it? The lines with X's on them are Bragg flow, and the lines with pluses on them are PFLOTRAN. And actually what you're seeing here is X's and pluses falling right on top of each other. So these, the two lines are nearly indistinguishable in every single case. But how much difference is there really between them? So we went ahead and applied our time averaging integration, and then plotted the relative difference versus the absolute difference. And this line right here is a 2% relative difference, and you can see that the difference is less, it's less than 1% for every single one of the lines on this horsetail plot. So now I'm just showing you the relative difference versus absolute difference for waist area liquid pressure in, from left to right, replicate 1, 2, and 3 in scenarios 2, 3, and 6. And the only thing that I want you to get out of this plot is that for all 900 of these simulations, there was a less than 1% difference in the Bragg flow and PFLOTRAN results. So this is a similar plot for the borehole Calabria liquid flow, time integrated difference. And again, we're plotting relative difference versus absolute difference for replicates 1, 2, and 3 in scenarios 2, 3, and 6. And because differences in pressure and saturation propagate through the calculation of flux, largely through propagation into relative permeability, we gave ourselves a larger threshold before we're going to worry about the relative difference between the two solutions. And in the case of borehole flux, you can see that all of the differences fall below about 10%. So another way to compare the two codes is just to look at the uncertainty distributions across the replicates. And here we're looking at volume average liquid pressure as a function of time in replicate 1, scenario 2 in the waist area. So this is the same horsetail plot that I showed you earlier, but this time it's plotted as uncertainty distributions. The red boxes are PFLOTRAN, the blue boxes are Bragg flow. They're plotted a little bit wider so that you can see both at once. So we have the 25th percentile, the 75th percentile, and the median, and they all fall just about on top of each other. And even out here with the outliers, X's are Bragg flow, pluses are PFLOTRAN, and again, they're all falling right on top of each other. Here's a similar plot for cumulative flux up the borehole. And in this case, because it's only one time value at 10,000 years, I was able to plot all of the replicate scenario pairs on one plot. So this represents actually all 1,800 simulations. Here is scenario 1, in which there is no borehole, so there is essentially zero flux up those cells. Scenario 2 is right here. Scenario 3. Here's scenario 4 and 5, in which most of the borehole fluxes are downward toward the repository. And here's scenario 6. And again, what you should get from this plot is that the 25th, 75th percentiles fall right on top of each other, as do all of the outliers. So in summary, I think we met our objectives. The comparison of PFLOTRAN's new WIPP flow mode to Bragg flow demonstrates that two-phase immiscible flow and all of the WIPP-specific process models are correctly implemented in PFLOTRAN. PFLOTRAN performs robustly over the entire sample space used for WIPP-PA flow calculations. And the differences between the Bragg flow and the PFLOTRAN solutions are sufficiently small that the transition to PFLOTRAN by itself should have minimal impact on PA calculations. So right now we do have underway a similar comparison for radionuclide transport, a PFLOTRAN nuts comparison, and Jen is heading that up. And we're working on developing a small 3D repository problem so that we can start working out any issues that are going to occur in the transition to 3D.
Thank you, Emily.